So I have this recording of the lecture on the topic active power frequency control. It is part 2, where we will have the discussion on the characteristics and performance for regulation of frequency. This recorded lecture will be a part of scheduled lecture that we had it on 4th and 5th, which I could not have it for you. So we move on to the lecture slide. So this is the one where we discuss the characteristics and performance for active power and frequency control. And so if you recall from the previous discussion that we had in one of the lecture. So if you refer, this was the block diagram that we had considered for the governor with a speed droop. So you had the turbine, the measurement of speed, reference speed here, and then speed deviation at this part. And we had the speed droop applied, and then the correction on the signal through the P proportional controller and integral controller, which was given to the actuator for steam and water inlet to turbine. This was represented in this way as a block diagram. So you had the, in fact, it is this one. So you had speed deviation, then the proportional integral, then you had the, you can say, the feedback. So it is this one here from the output of the actually this signal. So you had this, and so this part is represented here. And then we had reduced this complete representation as this one. So here we had the governor with the speed droop included. Now, if in this case, the governor regulation was based on the droop characteristic applied on the governor. Now, next part which we want to have here, it is how to regulate the output power of generator. So we want to formulate a relationship between the speed and the power, and thus the load, you can say, and thereby we want to regulate the output power of the generator based on the power set point. So that is how we should decide that what should be the output power from a generator. So we want to say it as a load reference set point here, this one. And so we had from the previous block diagram, we had included this term here, load reference set point. So it is this comparator, in fact, as you can see here. So we have added a comparator here in this case, and so that will work as a to achieve a load reference set point here, and thus regulate the output power of a generator here based on the set power set point here. rather than just as a speed droop or the droop characteristic. So in a block diagram form, this is slightly modified. So we have it here. So reference, or this is the speed deviation, the droop, in fact the gain, and the load reference. So if you remember, we had the droop defined here. That was the R, that is delta F by delta P here. So this one, the load reference is the delta P. You can say how much change in the power you apply. So that's not only the speed deviation against the load change, but also how much power change you want from the generator. So that means you also include not only the droop characteristic, the speed droop characteristic, but also the regulation in terms of the output power for the generator, and that's we call it at load reference or the power reference set point here. So this is the same block diagram that we had it here, this one. So thus this was the complete block diagram representation in the reduced form with the for the governor with the load reference control applied here. So with this, output power for a given generator can be adjusted to any value that will be through controlling the reference set point on the power set point. So that means we want to adjust the output power of a generator according to the reference change in the power you want here. And if you have several units, several generators operating in parallel, then with the adjustment of droop, that will allow a proportional change in the output power for a generator. So with that, whenever you have some load changes, so with one way is that you change the you adjust the droop characteristic here, so that proportional amount of power can be regulated whenever you have sudden disturbances. That means from the load side. Another one, we can have the adjustment of load reference set point, basically, which will determine what will be the output power for a given frequency here. So in fact, as you can see, here we have on this axis the frequency and then the output power change in percentage. So as you can see, here on this axis we have the frequency, and then on the x-axis it is the output power in percentage. And we want to understand how does the load reference set point will influence the change in the characteristic here. So we consider for 60 Hertz with each characteristic corresponding to droop of 5%. So you have a characteristic A, and which results in zero output power. And if you refer to characteristic B, that corresponds to 50% output power. And then characteristic C, which which corresponds to 100% output power here. So what we basically observe that there is a shift in the characteristic basically, which is in parallel, because we have considered that means the slope of the characteristic, it is constant, it is with 5% true, but each of these characteristics corresponds to how much change in the power it should have. And so that means for A characteristic, it 60 hertz, it will correspond to 0 output power. For B characteristic, for with the 60 hertz, it will correspond to 50% output power. And with the C characteristic, what you have at 60 hertz, this will correspond to 100% change in the output power here. Maybe you can have a little bit more description about this shift in the characteristic on this slide. So you have, let's say, 60 hertz with the output power corresponding to 150 megawatt, and you can say this is the initial set point. So initial set point 60 hertz gives you 150 megawatt, and let's say that this characteristic can be shifted upward or maybe downward on this side, and then you have an area defined, a rectangular area. So it will be between this range, you will have the operation of the generator, and thus the operating point. The operating point can lie up to within this range or on this side here, within this shaded area. So if we have this characteristic is for 5% true. So if we have the change in the power set point to 160 megawatt, initial operating point was 150 megawatt. So here you have 150 megawatt corresponding to 60 hertz here. If the set point, if the power output set point is changed to 160 megawatt here, so that means 10 megawatt delta P. So it will, the characteristic initially, it will move this direction. So you have direction of the movement. So it will change to 160 megawatt here. So remember that the correct change in the characteristic will be always along this line. So the operating points, the shifts from initial point along this characteristic, along the drop characteristic up to this one here. So here, this is the 160 megawatt, and temporarily the change in the frequency will be this value, 59.9. So temporarily, this will be the operating point here. And with the correction applied, dial omega and the change in the output power applied, that means regulation applied towards the output power change. This operating point, again, it will shift. So now with the change in the power of 160, in fact, delta P, that is 10 megawatt, you will be able to get the frequency of 60 hertz. So you now here, the operating change in the point was in this way direction. This was the temporary operating point. And then with the correction, that is the regulation applied, the operating point will shift here with the output power of 160 and the frequency of 60 hertz here. So thus the characteristic shifts in this direction, then again goes back. So with the change in the power of up to 160 megawatt corresponding to 60 hertz, it is achievable here. Similarly, In this figure, it is shown for change in the output power. It is reduced value. Delta P is reduced by 10 megawatt from the initial point. So this was the initial operating point, 150. Frequency was 60 hertz. And now if the delta P is reduced, so thus the change in the characteristic will be along this. So this will be, sorry, along this direction. So here it is what you have it, this will be the temporary set point here. And with the regulation applied, the final set point will be this one. So now it means we have the reduced power, generation power as per the reference set point 140 megawatt, and for that operating point it will correspond to 60 hertz here. So thus we had the characteristic, as you can see it moves this direction. If you have 160 megawatt, so the characteristic move this direction, then again it is to this point. So that was the point, operating point here, which was this one. And if in case if I consider 140 megawatt change, so the direction of the movement along the characteristic, it was this one, and this was a temporary value, and then it changed to something this one here. It is this one. So oh sorry, so this was the initial operating point. It is this one, and for 160 megawatt it is basically this one. Actually, I must say it is this one, this area. Yeah, right. But this is the that's why it forms a complete operating region here. So you can have this curve either shifted upward up to, it can be, I mean to say here, it can be, sorry, this, or maybe it can be up to something like this. Yeah, so thus the characteristics can be shifted downward or maybe upward here from the initial operating point here. So next one here in this figure, the relationship between the load frequency characteristic is and the droop curve is shown here. So this is the initial operating point, and if you have the change in the generation, so thus the operating point will move along this direction here. And in fact, it was this one. It will move up to this one. And then, in fact, when the correction is applied, second step, it will move up here. So this will be the final point. So in fact, that's the load frequency relationship. Basically, it corresponds to little bit this with the second step applied. It will be not exactly the one which is as here is, but it is basically slightly, it has some slope is not exactly 90 degree basically, yeah, but it is little shifted uh, 90 degree. So that refers to the load frequency relationship and the droop characteristic that we have it here. So it means that this relationship and the droop curve, they form a non-linear relationship between themselves. So here, what earlier, if you refer the droop characteristic, what is shown here for 5% droop, it is basically a line here, a straight line. But in for actual turbine, these characteristics when you have, so it can be in different form. So the first line, the first characteristic is the ideal characteristic, which we have been discussing. But the second one, which you have it, this one. This one is from steam turbine, because in case of steam turbine, you have several number of valves, and that means sets of the valves. They will correspond to definite amount of change in the output power here. So this could be one set of the valve, it could be second set of the valve, third set of the valve, and final set of the valve, so as to get the 100% output power. So you can say each section of the curve here, what you have, that is from one control valve, you can say. However, for hydro turbine, which you have it this one, the third one. So for the case of hydro turbine, you have a single gate. So you single gate operation. So you have this type of this shape of the characteristic here for hydro turbine. So this next to here, we want to discuss the combined characteristic, regulation characteristic, that we call it as composite regulation characteristic. And we start with the for multi-generator system. So we say that we assume that all the generators they are coherent and against the system load changes. So thus the characteristic of all the generators what you have, they will be very similar against the disturbance. So here we will consider an equivalent generator, which it will be an equivalent model for several generators, and thus we take into account the inertia constant of individual generating units. So we write in this way. So what is the equivalent mechanical time constant, VQ, and that is twice of inertia constant, and thus it will be twice of all the generators, individual generator inertia here. So we can say that it can be change in the output power from one turbine, second turbine, and several of them, and against the common load disturbance here. And thus the in terms of equivalent model for all the generators representing one generator, equivalent generator, we can write in this way. So you have equivalent inertia here for the system, and then the load damping constant, and that is the frequency here. Then here we are discussing the composite regulation characteristic. So this part is for the generator side, and then if you take into account the system load, which with the frequency, system load changes with the frequency. So that means the frequency sensitive load. So with the load damping constant defined for frequency sensitive load, we can say this is the amount, the change in the power from the frequency sensitive load, which is given by what is the load damping constant times the frequency, the change in the frequency. So when you have load increase, then the frequency will drop due to the governor action, governor droop characteristic here. And then if you consider the frequency sensitive load, we have discussed earlier that because of the frequency sensitive load, the combined effect, the combined impact on the output power generation from the generator, it is slightly reduced. So what you have it here, the net reduction in the frequency, however, it will not be as high, and thus the steady state frequency deviation you can write in this way. So what is the change in the load, and then what is the regulation characteristic for individual generators. So we can formulate what is the equivalent regulation for all the generators. Basically we are obtaining the equivalent for a equivalent generator. It is this one. So we have the equivalent regulation plus D, and this is how we can define the equivalent regulation. And then we define one factor here, which we call it as frequency, composite frequency response characteristic here, which we write it as ratio of power to hertz. So thus what is delta P and the frequency. So this is ratio of megawatt to hertz. And this sometimes also referred to as stiffness of the system, how strong the system is with the change in the power and frequency here. So this composite regulating characteristic is basically equal to 1 by beta here. So this is how we have defined the beta, and that is equal to 1 by RAQ plus D here. It is this part. So composite regulating characteristic will be the inverse of beta term here. So if we recall, under a steady state condition, frequency and then angular speed here in per unit steady state value, they are equal. So from the relationship what we had last in the previous slide, so it is this one. So here we want to understand the combined effect of regulation basically. One is from the droop, and then another is from the frequency sensitive load here. So how does the overall frequency deviation will take place because of this disturbance applied. So we consider to understand the composite regulation characteristic with the speed droop characteristic here from the turbine governor side and the load damping constant side here, or the load damping. So let us consider that we have an increase in the load by this much amount. So because thus if you have a sudden increase in the load of this much amount, we expect that output power from generator should increase because the load has increased. So that's the output power from generator should increase. Why? Because you will have the governor in action. So it will be the governor which will regulate the output power from the generator, increased output power. But that increase in the power from the generator can be compensated with the load damping effect because of frequency sensitive load, and as a result you have basically reduction in the uh, load and thus the generation basically from the output of the generator. So what is deferred here? Because of the load increase, this is the initial that means the nominal frequency here, and when you have increased load, so the frequency will dip. So that's the dip in the frequency, that means this one, delta F here, frequency drop. Frequency drop will be, it has a negative slope, and then based on speed drop characteristic here. So we can write this one. So this is basically what is, if you look at the slope of the curve, it is basically the ratio of output power from the generator and the delta F here. So it is this term. But for this change in the load, which corresponded to this much, there is a, as I said, reduction in the, it is basically the load reduction, or the, in fact, the generation demand. In fact, the how much change in the generation is demanded by this change in the load, that is something reduced. So with the load damping constant given by this, so if you remember the frequency sensitive load like dynamic load, induction motor loads, the output torque, because when you have the frequency has reduced because it is a composite. So let's say load has increased, so, but thus the frequency reduced, thus the output torque of the motor also corresponding reduce, and thus that we call it as the load reduction because of frequency sensitive load. And this will basically have an impact and given by this ratio. So it has a, you can see it will be this change in the power or the reduction in the power which is to be met by the generator for this load change. So because of the frequency sensitive load presence for this load change, the output power generation is only up to this amount here. So if I say there had not been any frequency sensitive load, then for this much change in the load, this should have been the change in the power. The change in the power from the generator could have been up to this value. It could have been up to this value here. But because of frequency sensitive load, the output power from the generator which is required, it is only up to this value here. So thus it is said that because of frequency sensitive load, there is a load reduction For example, if I say that uh, there was a load increase, so the load increase was something 50 megawatt. Yeah, that was the load increase here on the generator. Total load increase was 50 megawatt. But let's say that because of composite load characteristic, so that means some static load and some dynamic load. And let's say because of dynamic load, this change in the power from the dynamic load, it corresponds to something 5 megawatt here. So because of load frequency drop, the load reduction from the dynamic load, basically it is something 5 megawatt, and thus the generation change, which is required against this much change in the load has to be something difference of the two, so that it will be this generation change has to be something 50 megawatt minus 5 megawatt. So this should be corresponding to delta P. So it means that we will have the generation output regulation of just 45 megawatt due to presence of dynamic load, that's the induction load. So you don't have to have the output power regulated exactly equal to the amount of load change here. So that's the dynamic load is one way beneficial advantages when we want to have the output power regulation on generator. So the same thing is explained here. So you can see, so you have the generation, and thus the generation change in the power will depend upon what is the two characteristic here. So what was the delta P and what was the delta F here? So delta F and delta P, that will correspond to speed to characteristic here. So this will be the change in the power from the generator side. But since here we have the composite load, so this is the composite load. So we have some amount of frequency sensitive load. So, and thus the reduction in the load from the frequency sensitive load, basically, it is load damping constant times delta F here. Thus the total load is this one. So this total load, what you have it here, is actually delta PG minus delta PD, how much change you have it here. So delta PG is minus 1 by R delta F here, and delta PD, it is D delta F here. And this now the delta F will be given by this relationship here. So the next one, here it shows uh, the different time response characteristic of the generating units, and here it is shown for a step increase in the load as you can see on this axis, it is how does the valve gate position with respect to time, and then how does the power from the turbine with respect to time, and then the speed deviation with respect to time. So we have a small step increase in the load. So for the different types of turbine, hydro turbine, turbine without reheat, turbine with reheat, these curves have been shown. All the three curves, that means how does the valve or the gate position, valve in the case of steam turbine or gate in the case of hydro turbine, how it will vary. Then for the case of output power, mechanical output power from the turbine. So as you can see for these three, hydro turbine without reheat, with the reheat, and you can see this one. So this characteristic, what you have it here, because of the non-minimum phase characteristic of hydro turbine. So we have this one. And you can see the hydro turbine is comparatively slower. But and again, if you have without reheat, so again, the response, you can see it is faster. But if you have reheat, then the steam turbine, it is comparatively slower with respect to the without reheat steam turbine. Now, if you have the speed deviation, then you can see the solid line with the reheat. So it is this scope, and then without reheat, what you have it this scope, but then you have it for hydro turbine, it is this scope here. So this is the, you can say, the how does the valve or the gate or the output power or the speed deviation for the different types of turbine takes place whenever you have the step load change. A little bit more about it, what is shown here. In this case, we have shown the frequency, and this is the curve what you have it without primary control. So the from 50 hertz, the frequency, let's say you have what you have it here, it deviates and it drops. You can see it less than even 46 or something. But if you have with the primary control action included, then this is the curve for what you have it without reheat, and this is the curve with reheat. And for the case of hydro unit, and here it shows what is this amount of step load change here. So with this much step load change applied, the frequency deviation for each of the different turbines with primary control action, it is deferred here. So you can see where without reheat, okay, the deviation is much lower, and again you can see that the response is faster, but with reheat you can say deviation is more, because this is the nadir here, the maximum frequency deviation here, and then response the frequency settling down to the final value. Next, if you consider for hydro turbine, you have little bit more dip here in the frequency and then settling down to the final value here. But you can see that but here it is along on 48 hertz scale. So this is the frequency deviation steady state value here. So this curve, what you have it shown, it is on this axis we have the governor or the load response, and here you have the frequency, which is will be for red curve, and then these two will be you have it for red curve. So at this where you have at this instant of time, the power is 1600 megawatt, which corresponds to about 60 hertz here. And then when you have the load change applied, frequency dips here. So what you find that at this point, this one, you have nadir, that means the maximum frequency deviation, you get it somewhere here. So here it is something generation and load response equal, and then with the regulation applied, the frequency will settle down up to this value, so 59.9 hertz here. So what is shown, the governor response, this will be the output power, that means the control signal from the governor, how it will change here. So it starts increasing the governor response signal, but as soon as the frequency deviation takes place with the load increase. So you have, this is the response here. And then this was the basically the load increase, the load response, and this red curve was the frequency, this characteristic frequency response characteristic. Now this for the governor, the load response, it has been shown for an ERC. It is Electricity Reliability Council, which is as per NERC, frequency response is defined as how much change in the generation loss divided by what is the frequency point at A, and what is the frequency point at B here. So that means frequency response characteristic they define in terms of these two quantity. So with the primary, maybe I will stop here and then we will continue later.